Let's start to look at the solution of the first challenge, that was the one to solve a system of linear equation. And the first thing to do is just to type the coefficient matrix and simply create a matrix to the Numpy array using Numpy, and the first row is corresponded to the first row in our system answer. Then we create the vector column for the coefficient term. Here is just also created as a list, but it doesn't matter because it's going to be converted when we are doing the dot dot. We are in vertex the matrix. We can also ask if you want the shape and what is the inverse matrix A, and then we can just obtain the solution typing inverse of the coefficient matrix product with the constant terms vector. The solution should be 1.66, 0.33, 0.66 from an analytical solution. We can just print our solution, and we can also recognize the structure that is -5, 1, -2. The other possibility will be just to use the linear algebra submodule of Numpy and then solve, and that one is simply the matrix A, B, and then here we are just taking only the first 3 digits as a solution. We can also do exactly the same here. Sorry about that. And we can just see that they are exactly the same. And we can compare elements by elements. So this is the solution, and we obtain a vector that is true. So let's go to see the solution for the second challenge, the one that describes a growth population, where the number of children at the future step coincide with the number of adults at the present time, and the future population of adults will be the sum of the adults at the present time plus the number of the children at the present time. Every children evolve in one time frame into an adult. This growth can be written in a matrix terms, where the future is h, the present, where h is the matrix that just contain this coefficient 1, 1, 1, 0. So, first of all, import Numpy and matplotlib, because as you see, so some of the question regard the plotting, different function. And the first things to do in whatever physical problems you are trying to solve numerically is to set up your initial condition. And here we have 3 different conditions, initial parameters. One is the total number of iterations that we are doing, that is Tmax, and just set that one to 10 as suggested in the text, but that one can be later on changed. The initial population we do not have any adults, and we have only one child. And then we can define a vector for our population that is initialized to the number of adults and the number of children. And it's just as a way to recreate this kind of vector, this kind of matrix. Then we are defining the matrix H, and that one is to the object. First row was 1, 1, second row was 1, 0. And it's also convenient already to calculate the eigenvalues and eigenvector, especially the eigenvalues, because that one will be our reference point. And we can use the submodule linear algebra and the built-in function eig, and that one will provide us a tuple that contains both the eigenvectors and the eigenvalues. Our reference point value for the subsequent calculation that we have to do is the positive eigenvalues. And if we are running here, we can find that we have two different eigenvectors, and the reference values is this magic 1.618. That is the golden number. As expected by an analytical calculation of the eigenvalues. Now we can before that, here. Now we defined a new matrix that has the length of our time range, and we define it as an empty. And now we are started to do loop over the time, because that one is an evolution. And we remind that is a discretized time, and the new population will just coming from the equation that we have written here, and so will be dot, so the product between the matrix and the population, and the total population is going to be at every time t is going to be the sum of the adults and of the child. Now we can also compare, and if we are writing per each time step, here we will see so our total population. Let's now compare the growth rate with respect to the reference value, the golden number that we have calculated before. For doing that, we are creating an empty vector, or with a certain constant volume, doesn't matter, and then we are reassigning it for different time step the ratio between the adult population and the children population minus the reference value. And for this factor we are asking, so 1, it is lower than a given threshold, out of the loop of course, And then we can also plot both the total population and the growth rate. The growth rate is that one is green, and you can start to see that it's depending on how many iterations we are doing, so we have not reached yet a good convergence. But we can also put a stricter criteria, of course, and so that one means that we are still out of this convergence. On the other hand, if we are plotting the total population, we are happy to see this exponential growth that is expected. So, but if we want to get this better convergence, what we can do? So the simplest things will be just to increment the number of time steps. Sorry, here. Increment the number of time steps. And here we start to see that many of them are starting to be true. And of course, so the population is rapidly changing. I would also to comment on a different possible solution. So the same scheme, setting up the initial condition, the total number of steps, the initial order and the initial children population, and the array that define the initial population as adult and children. Then the calculus of the eigenvalues of reference of our matrix H. And we can also create an empty vector array for that contains the growth rate of the population, and that one is expected for the population itself, and that one is going to be an int. So that one is going to be the case. And here we can use the linear algebra submodule and the matrix power of the matrix H to the subsequent time iteration I, and of course make a matrix product with the initial population. The total population can be put in append, so this new value, along columns, so we are just creating a bigger and bigger array. And the total population outside the loop will be calculated as a sum along the rows of the array pop. If you are running this part, we start to see this smooth value, and that one is the total population versus the time step. Now we are comparing with the growth rate and with respect to the reference value. So what we are taking is the ratio between adults and children with respect to the value, and here we have just to be trick enough not to consider the first two steps, simply because otherwise we are just not to have any zero that in our population. And that one is the difference between our growth rate and the golden number, and we started to see that is oscillating a lot at the beginning and then finally smoothing down. The same object can also be calculated in a different way, in creating a vector now with time step -1, and just calculated the total population at time I and divided by the total population at the previous time. And then of course reupdating the growth rate as the difference between this ratio minus our reference value, and that one is the plot in red, where again we have a similar behavior. These two codes we see that you have some good hints. That one, how to use the linear algebra a submodule both for calculating the eigenvalues, but also for this tricky matrix power for the evolution of system, where we are just applying this method. Consequently, also thus to have the dot built-in function of Numpy for solving a system of linear equation. Thank you. Bye.